Okay, folks, let's get started. So let me start by just reminding everyone that there's some extra lab hours open today. So today from 3 to 5, the lab will be open, and I'll be in there to help folks debug. And then also tomorrow from 11 to 1, the lab will be open. Those times are what they are, incidentally, because this is the week that we start sharing 238 with 2300. So those are the times that the lab was unoccupied and we could get in there. So most folks in the class are still working on cricket detection, which was the checkout for last week, and that's okay. So what I would ask you to do is to try to get cricket detection finished by the start of this week's, your scheduled lab section for this week. So if you're in the Wednesday afternoon lab section, please have your cricket detection checkout done and checked out by myself or by a TA by the start of that lab section. This week's lab section, in this week's lab, you'll be asked to implement the synchronization algorithm. So after last week, you will have given your cricket a voice. You can synthesize crickets, and it has ears. You can hear other cricket chirps. And the final piece of that is to get the two to interact. So when you hear a cricket, you do something. And the thing that you do is change the timing of your chirp a little bit in order to affect synchronization. I was going to talk about that synchronization algorithm today, but over the weekend, I thought quite a bit about how best to use this particular lecture, because it occurred to me that most folks are kind of still in the cricket detection mindset and aren't really thinking about synchronization just yet. So I didn't want to go over material that people are sort of half listening to because they're focused on last week's checkout. So I thought what we could do instead is a review session. And I thought that this would be productive. Incidentally, if you don't like this, just let me know and we won't do it again. But when I was a student, the one thing that I liked about tests was the review sessions. There was something about seeing all of the content that had been introduced again a little bit more quickly and in context with one another that helped organize all that stuff in my head. And if this class gave tests, which it doesn't because it doesn't make sense for a class like this, now would be about the time where I would be thinking about giving a test. We're starting week 4 of the semester. We've gone over a lot of content, and it occurs to me that perhaps it would be productive to just go over that stuff again a little faster and in order. The first time you would have seen it, it was brand new, but now you've had the opportunity to play with it in lab a little bit, so perhaps hearing me talk about it again will be helpful. And incidentally, I'm also happy to use this time in this lecture to answer any questions that folks have about lab checkouts, right? The purpose of these lectures is to help you in the lab. So I think this is the most helpful thing I can do today for you in lab. If there's other stuff that you want to talk about, just let me know. Okay, any questions for anyone? Yeah.
Really quickly, can we go to a lab section that's not ours to finish?
Yes, absolutely. And I'd encourage folks to sort of perhaps make that a routine. The only lab section that I ask for you to perhaps avoid is the Wednesday night one. And it's just because that one they scheduled us simultaneously with 2300. So I believe every single seat is full. But all the other lab sections, there's some extra benches. And if you're not actually enrolled in that lab section, it'll be a little bit first come, first serve. But in past semesters, anyone that's wanted to show up and work, there's generally been a place for them to work. So yeah, do please come to other lab sections. Other questions? People in the waiting room. Hold on. Okay. Then in that case, what I'm going to do is start reviewing the stuff that you've seen before, but maybe now you're seeing it and it looks more familiar and friendly than it did the first time around. So let me start by just reminding you of the levels of abstraction of hardware and software in this system being the RP2040. This is a diagram that I showed you. We spent a bunch of time looking at this diagram in the first week of lecture. And what this attempts to illustrate is each of the software levels of abstraction and how those levels of abstraction interact with one another and with the hardware. So what I'll remind you is at the bottom of this hierarchy is all of the RP2040's internal hardware peripherals. So this includes things like an SPI channel, some hardware devoted to generating PWM signals, timers, a real-time clock, all this stuff, which I'll just clarify incidentally because I've detected a little bit of confusion about this. These hardware peripherals are separate from the processors. So we'll look at a diagram in a moment, but I'll just remind you that the processors are, they exist within the RP2040, and then separate from the processors are all of these hardware peripherals. And from the processors, you can configure and control those hardware peripherals, but these exist outside of the ARM processors. I'll talk about that a little bit more in just a moment. So at the lowest level, we have all of this hardware, these hardware peripherals. Fundamentally, we configure and control these hardware peripherals by manipulating the values of registers. So all of you at this point have looked through the data sheet for the RP2040, and what you will have discovered is that at the end of each chapter of that data sheet, particularly the sections associated with these hardware peripherals, there's a whole list of registers. And if you go investigate any one of those registers, it'll describe what each bit in that register configures or controls, or alternatively, what information each of those bits is giving you about that particular hardware peripheral. So for example, there would be some control register associated with the SPI channel that sets up things like the baud rate, sets up things like the clock phase and clock polarity. And there would also be some status information in the SPI registers that indicate things like the transmission is complete. So you can go check the value of that register to see when the hardware peripheral that you've asked to do something is done doing that thing, right? So all these registers, they're just places in memory that the system interprets in a special way. But they're just places in memory with addresses. And we could, if we cared to, if we were really masochistic, we could do all of our programming of the RP2040 strictly through register manipulation. But the Raspberry Pi company, and essentially every other company that makes microcontrollers, recognize that that's really cumbersome. There's thousands and thousands and thousands of these. And sometimes it's the case that you modify one register and that implies modifications that you have to make to some other register elsewhere. The behavior can be coupled. So in order to make development with the RP2040 and with microcontrollers in general more tractable, it's often the case that the company will put together an SDK. SDK stands for Software Development Kit. This, for us, takes the form of a whole bunch of C libraries. So it instantiates a bunch of C functions that you can include in your source file and call. And if you go look at the implementation of any of those C functions in the SDK, what you'll see is that what all of them are doing is just manipulating these registers. So it's abstracting the register manipulations into more readable function calls for your convenience. And then the highest level of abstraction is proto-threads, which we spent some time talking about. This is a lightweight stackless threading library. This isn't a Raspberry Pi company thing, incidentally. This threading library was written by a guy named Adam Dunkels, but it ports to the RP2040 just beautifully. And we use that to organize our application code. So this makes it very easy for us to set up our code in a modular way. That is to say, we can add new stuff to our applications relatively easily if we're using a threading environment. It also makes it really easy to set up concurrent programs, which is what all of your projects in this class are. Concurrent programs being applications where you have multiple things happening sort of simultaneously and at different rates. You have conditional code that you only want to run when certain conditions are met. That's doable without a threading library, but the more cumbersome that state machine gets, the more difficult it is to add functionality and to debug. The threading library just makes this much simpler. So these are all the levels of abstraction. We have the internal hardware. This is no-kidding hardware. Fundamentally, that hardware is configured and controlled by manipulating registers. Those register manipulations are abstracted by the C SDK, and then we organize our application code using a threading library called proto-threads. And this is an image from the RP2040 datasheet that we spent some time looking at. But this is giving us a schematic view of all the hardware that's contained within the RP2040. So, for instance, we have up here processor 0 and processor 1. These are the two ARM Cortex M0 processors that you can program in the RP2040. Each of these share 26 interrupts. You've interacted with a few of these interrupts at this point. And each of them also communicate to this SIO, which I'll just remind you contains all of the peripherals to which each of the processors require low latency access. So for instance, access to these hardware spin locks that we use to control access to shared resources between the processors, access to integer divisors and interpolators, and access to the GPIO registers. And then there's a bunch of other stuff in here as well. So in addition to the processors, we have DMA channels, 12 of them. We have a bunch of SRAM. We have a USB interface. We have ROM. This is where the bootloader lives that allows for you to program this thing via that USB interface. That logic lives in this ROM. There's a cache here that communicates with a QSPI channel here that goes to the external flash. Just remind you that your program code on the RP2040 is stored in external flash memory. And then there's a QSPI channel to some onboard cache so that it can store some code locally for faster execution. There can be a funny consequence of this, incidentally. If you time your interrupt service routines, which is to say you time how long it takes for you to, when the condition for an interrupt is satisfied, how many cycles does it take for you to get into that interrupt service routine? And it's going to take some non-zero number of cycles because the system has to store its state so that when it comes back out of the interrupt service routine, it can resume what it was doing. But you'd expect for it to take, I don't know, on the order of 50-ish, 100-ish, something of that order. It can be the case that if you go and time the amount of time that it takes for you to get into an interrupt service routine, it takes way longer than you might expect. Does anybody have a guess for why that could be based on the way that this is arranged? So in the cache, we're storing the code that's running for fast execution. If we hit an interrupt and the code that interrupt runs hasn't been cached here locally, we have to go get it from the external flash. That can take some time. And there is actually there's a compiler directive where you can tag a particular bit of code and say, I would like to please store this in cache. And that mitigates that problem. But it's just sort of it's an interesting thing that you might observe if you start timing your interrupt service routines. There are also two PIO coprocessors. These we'll talk about in detail probably in 2 weeks. But as I mentioned briefly previously, you can write programs for each of these two coprocessors in assembler. There's a custom assembler called PIO assembly for these two coprocessors. They are really limited in a really fun way. The program that you write for either processor may not exceed 32 instructions. That's as long as your program can be for either of these two things. But what's fascinating about them is every one of those instructions has guaranteed single cycle execution, and these PIO coprocessors can talk to all of the GPIO ports. And they can talk to things like the DMA channels. So what this enables, as we'll talk about in just a little bit more time, is it allows for you to build custom high-speed communication interfaces. This, for example, is what facilitates our communication with the VGA screen. As some of you might be aware, to communicate with the VGA screen, the clock line for that interface is 25 megahertz, just really fast. You can implement that on other microcontrollers, but on a lot of other microcontrollers, doing so ends up sucking up pretty much all your CPU time. So communicating with the VGA screen and also doing some sort of interesting graphics routine can be difficult. You can run out of cycles. In this case, because we've used these PIO coprocessors to do all of our communication with the VGA screen, we can write to that screen as fast as we can manipulate the values in an array. So writing to the VGA screen becomes really fast for us because of these PIO coprocessors. And then the other thing that this is showing is the whole library of hardware peripherals. So we have two SPI channels. You've been interacting with one of those SPI channels to communicate with the DAC. We have a pulse width modulation peripheral here. We'll use that in lab 3 in order to control some DC motors. Two UART channels. You all have interacted with one of these in order to print data to the console. An internal timer. You all have used this at this point to set up your repeating timer callback function for audio synthesis. There's a real-time clock, which we won't use in any of the labs, but when we have some time, I may talk about just a bit. If you want to schedule code for execution way far out into the future, this real-time clock is a nice alternative to the internal microsecond timer. I'll just remind you that this internal microsecond timer, it's 64 bits. The 32 least significant bits live in one register, and the 32 most significant bits live in another register. So the amount of time it takes for that full 64-bit timer to overflow is like 500,000 years. But the amount of time that it takes for the lower 32 bits to overflow is like 72 minutes or so. So if you're trying to schedule code for execution farther out than about an hour, the real-time clock is a reasonable alternative to the internal microsecond timer. An alarm clock, for example, right? If you're trying to build some sort of an alarm clock, that might be nice. There's internal there's two I2C peripherals. We'll use this too in lab 3 to talk to an IMU, an accelerometer and a gyroscope, an ADC and temperature sensor, which you all are familiar with at this point, and then some other sort of system level stuff, a watchdog timer, and then some other system level stuff. And what the green is indicating here is which of these peripherals can communicate to the GPIO ports. So it makes sense, for instance, that the SPI channel communicates to the GPIO ports because we're building an interface to some external thing. So it needs to be able to talk to the outside world. Same for the PWM and all these things. And like I mentioned, the PIOs can talk to all the GPIOs. And then there's some internal PLLs, which you will probably want to manipulate in lab 2 to speed things up to get as many boards as you possibly can. So this is what's inside the system. And I'll reiterate what I mentioned before, is just to clarify to folks that these hardware peripherals are separate from the processors. So when you enter main, and your main likely looks something like a bunch of setup and configuration code, and then maybe scheduling threads, or maybe an infinite while one loop or something. But when you're doing the setup and configuration of these hardware peripherals, what you're doing is you're asking the processors to issue bus commands to this external hardware. That is being received by this external hardware to change its internal state, and then it's configured. So for instance, the DMA example that we looked at last week, where the DMA channel was sending a sine wave out to the DAC, if we take a look at that code again, and we will in just a moment, what we'll see is that in main, we're setting up and configuring some DMA channels. So that's a bunch of being commands sent from one of the processors to the DMA to configure it. But then main exits on the processor, which is to say the processor is not running anymore. But we've already configured and set this up so that it can run even though the processor isn't running. Right? So I'm just clarifying that this stuff is outside of the processors. And like I mentioned, many of these internal hardware peripherals need to communicate to the outside world somehow. And the way that we get them to communicate to the outside world is by mapping their internal signals to the GPIO ports. And like on many microcontrollers, we have some flexibility as to which GPIO ports we can map a particular internal signal. Not total flexibility. We can't map any internal signal to any GPIO. But generally speaking, for most of the internal signals, you have your choice of a few. Which is nice because you may want to choose one GPIO over another GPIO because, well, perhaps you want to use GPIO 3 for I2C1 clock line, so you use a different GPIO for your SPIO 0 transmit line, right? So you can sort of optimize which signals are getting mapped to which GPIOs. It may also be something as simple as you would like for all of your wires to come out of one side of the board for mechanical reasons. Maybe you're building some sort of a robot where it really helps with the design of the robot to have all of your electronics coming into one side. And sometimes that might be possible with strategic choice of which GPIOs you map signals to. Okay. And I'll remind you that that SDK that we're using is also arranged hierarchically. And we spent some time exploring this. So mostly what you're interacting with are these two levels of abstraction. You are mostly interacting with the hardware support libraries These are in your source files. Every time you include a file that looks something like include hardware/spi.h or something like that, what you're including is, in that particular example, you would be including the hardware interface library to the SPI peripheral. So it's providing you an API for interacting with that particular peripheral. So it includes, a whole set of functions that abstract register manipulations for that peripheral. And then the other thing that you're interacting with are some of these higher level libraries that implement some higher level capabilities by wrapping some logic around some of the lower level hardware support libraries. So for instance, one of the higher level libraries is called something like Pico/time. And this implements things like a repeating timer callback function. So I'll remind you of this in a moment, but your hardware interface library to that microsecond timer, what that allows for you to do is set the value of those alarm registers that we talked about. And when you set the value of one of those alarm registers, what you're doing is you're saying, when the value of the lower 32 bits of the incrementing 64-bit timer match the value in this alarm register, then throw an interrupt, right? That's the fundamental lowest level capability. And then there exist higher level libraries that build upon that low level capability to do things like set up repeating timer callbacks, because the Raspberry Pi company recognizes that that's probably something that a lot of developers are going to want to do with that low level capability, right? And then at a lower level, at the lowest level, there's a whole bunch of registers. So if you crawl down the levels of abstraction of the SDK, what you'll find at the bottom is files that contain a whole bunch of pound defines that associate somewhat readable names with places in memory, right? It's just naming every register that exists in the RP2040. This hardware structs libraries then organize all those registers so that they represent the memory mapped layout of the RP2040, so that you can open up the struct associated with, say, the SPI channel, and it will contain as fields all of the named registers for the SPI channel in the order that they appear in the datasheet, which is really convenient. And then, generally speaking, these hardware interface libraries manipulate the fields of these structs. Questions about this? Okay. So let's see. Let's talk a bit about this timer peripheral. So this was the first peripheral that we talked about. And the reason that we talked about it first, let me see, I just want to open up timer. USB timer. The reason that we talked about it first is it's a really simple one. What do I mean by simple? I mean, there aren't that many registers associated with this particular hardware peripheral, and it doesn't do that much. What it does do is incredibly useful, but it's not incredibly configurable. So there's not a lot of bells and whistles for us to talk about. But I'll just remind you that the timer peripheral is a microsecond incrementing timer that's 64 bits. We just talked about this, but those 64 bits are arranged into two registers, one containing the least significant 32, the other containing the most significant 32. You can read the value of this timer, which some of you are doing incidentally for your chirp debouncing. In order to only detect one chirp per chirp, one strategy for doing that is, I'm core 0 and I detected a chirp. I can go grab the value of this 32-bit timer, and then core 0 is not allowed to detect another chirp until the value that it reads off this timer exceeds some threshold. That can introduce a bug a little bit in that the lower 32 bits of that 32-bit timer will overflow after 72 minutes. But I'm not going to ask you to run your demo for that long. So for purposes of this particular lab checkout, if you want to assume that the lower 32 bits of this incrementing counter are monotonically increasing, I'm okay with that assumption for this particular checkout, as long as you understand that after 72 minutes, that assumption falls apart. Okay, so what I wanted to look at were the registers associated with this. So let's scroll down here. Yeah. So So these are essentially all the registers associated with this peripheral. The ones that I just want to point out are these alarm registers. So I will remind you that there are 4 of these, alarm 0, 1, 2, and 3. Each maps to a separate one of those 26 interrupts that each of the 2 processors can see. So if you wanted to, you could go in and write a value to alarm 2, and when the value in the least significant 32 bits of the incrementing timer matches the value that you've placed there, you can configure an interrupt to be thrown. And you could write an interrupt service routine for that interrupt. In the checkout a couple of weeks ago, this isn't what you did. What you did instead, let's pull up the RP2040 C SDK. What you did instead was utilize one of those higher level libraries. Let me just pull it up. You utilized Pico time. Yeah. Pico time, which, among other things, implements a repeating timer. So you could build something like this. So at the lowest level, you can write to one of these alarm registers. When there's a match between the alarm register and the timer, an interrupt is thrown. If in that interrupt, you rewrote the value of the alarm register to be what you presently measure plus the same increment forward, you could schedule that interrupt to be thrown again. So you could, strictly through register manipulation, set up a repeating timer interrupt. The SDK has abstracted this for us, and this is what you've used in Lab 1. Under the hood, it's doing something like that, but it's making it easier for us to do the development. Okay. Questions about the timer? Okay. The next thing that we then talked about, after talking about the timer, was the SPI channel. And I'll just remind you that when you are hooking up an SPI device to some host device, generally speaking, there's going to be 4 connections. So you will connect, suppose that this is our RP2040, which is the device that is going to be the master or the main device on this SPI bus. We will connect the clock line to each device that we want to communicate with. In our case, we're only communicating with one DAC. In principle, we could add other devices to this SPI bus. Each one shares a clock line. Each one shares a MOSI line, MOSI standing for master out, slave in. So this is data going from the RP2040 to, in our case, the DAC. Each shares a MISO line, master in, slave out. This would be data coming from the device that we're communicating with back to the RP2040. You all have observed that this line is actually missing from the pinout for the DAC, and that's because we don't care about information coming back from the DAC. We're only sending it information. And each device that we're communicating gets its own separate chip select line. So in the event that we have multiple devices sharing an SPI bus, it's this chip select line that allows for us to point to a specific one and say, the data that's about to appear is for you and not for anyone else. So it should stand to reason that we don't lower the chip select line for multiple devices when we're doing a single transaction. Otherwise, we get confused. And the way that these transactions actually occur is we have some shift register that lives on the main device or the master device, and some shift register of the same length that lives on the slave device or the secondary device. And when we want to communicate from the main to the secondary device, what we do is drop the chip select line associated with the secondary device that says the data that's about to appear is for you. I'm about to communicate to you. And then what that device will then expect to see is a certain number of pulses on the clock line. The number of pulses that it expects to see is however long its shift register is. So for this image here, it would expect to see 8 pulses on the clock line. And then synchronously with each of those pulses, the data would appear on the MOSI and MISO lines. So data would get shifted out of the least significant bit on the main device and into the most significant bit on the secondary device. And the data would go chuk, 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 from the main into the secondary and simultaneously from the secondary back to the main device. So effectively there's a circular ring buffer set up between the main device and the secondary device. In the case of the DAC, we're doing 16-bit transactions, so the size of the shift register on the RP2040 would be 16 bits, and the size of the shift register on the DAC would be 16 bits. And as we've discovered, in the C SDK, when we're setting up and configuring an SPI channel, we are required to specify a couple of degrees of freedom. And in particular, so this is showing the timing diagram for an example 8-bit SPI transaction, so that you can see that this transaction starts by lowering the chip select line. That's indicating that a transaction is about to occur, and whichever device saw this chip select go low knows that that transaction is meant for it. And then 8 pulses appear on the clock line, and in this diagram you can see that the data on the data lines is valid at the rising edges of those clock pulses, and it's changing on the falling edges of those clock pulses. So if I'm the RP2040 or if I'm the DAC, and things are set up as shown here, then I will know that every time I see a rising edge on the clock line, it's safe for me to go get the data off the data lines. The data will be stable. The voltage on those lines will be stable. I won't attempt to go and check the data on the data lines at the falling edges because it may be indeterminate, it's changing. But the degrees of freedom that we have to configure when we're setting up an SPI channel are sort of represented in this image. So what this is showing is a transaction for which the clock is idle low, active high. That is to say, when no transactions occurring, the clock is just sitting low, and then once we start one, it pulses high. This could alternatively be the opposite. We could set up an SPI channel for which the clock line is idle high, it just sits high all the time, and then we pulse it low. Some SPI devices that you may want to communicate with require that. And you would learn if that configuration is required by looking at the data sheet for the device that you're communicating with. The other degree of freedom here is the data on the data lines, is that data valid on the rising edges of the clock or on the falling edges of the clock? And that too is not consistent across all SPI devices. It's something that you have to go look in the data sheet and see, okay, for this particular device, what's required. And by the way, you may have multiple devices on the same SPI bus, each of which require different configurations, in which case you would have to reconfigure the SPI settings between each transaction to each device. The system allows for that. You could do that. Questions about this? Let me just remind you what I'm talking about. So if we look at the course demo code, lab 1 incremental, let's look at the timer interrupt example. The configurations that I'm referring to are these in lines 66 and 68. You can see in SPI init, we are initializing one of the 2 SPI peripherals on the RP2040. You'll remember from that schematic that we just looked at from the data sheet that there are two SPI channels. And we're specifying that the data rate, the baud rate for that SPI channel will be 20 million bits per second. That number too we would get from the data sheet for the device that we're communicating with. And then we're calling a function called SPI set format that is specifying all those degrees of freedom that we just mentioned. So in particular, it's saying that there's going to be 16-bit transactions. It's saying that there's going to be a clock polarity of 0, that is to say idle low, active high, and a clock phase of 0, which is to say the data will be valid on rising edges, changing on falling edges. And the last argument here is order, which is to say shift out most significant bit first or least significant bit first. But as I read the data sheet, that's not actually modifiable. Yeah?
Why is the ring buffer necessary?
What's that?
Why is the ring buffer necessary?
Why is it necessary? I don't know if I have a good answer for why it's necessary. It's the way that it is. I know that that's an unsatisfying answer, but this is the way that an SPI channel works. Why was SPI designed in this way?
Like, I'm curious, like, is there any like applications where the secondary is trying to communicate back to the main, or like, is it like?
Are there applications where the secondary can communicate back to the main?
Yeah, or I guess in this case, the DAC, there really isn't like much reason to, right?
Yeah, so generally speaking, suppose that we're communicating with an SPI device that isn't the DAC. That is to say, a device where we may want to issue commands to it and also read data from it. Because SPI channels are set up in this way, what that means is, suppose that we want to, suppose, for instance, that we're communicating with, I don't know, some SPI temperature sensor, and we issue a command that says, I would like to acquire the temperature. So that would mean shifting some sort of a collection of data from the main device to the secondary device that the secondary device will interpret as a command that says, please load temperature into your shift register here. To actually then read that data back from the sensor, we have to send it data. And generally, usually you could just send it anything. You just send it junk. All that matters is that you're sending it the correct number of bits so that you're shifting the correct number of bits back into your receive buffer here. In the case of the DAC, this is disconnected. If you were to go check the data that was appearing in the shift register on the RP2040, there would be something there. And in fact, it would be, you know, if you have mapped MISO to a GPIO pin, which I believe all of you actually have, then it's whatever it's finding on that pin. Could be indeterminate, you know. Yeah.
If there are 8 bits you only wanted to send like sometimes, could you change the configuration for the main buffer to like flip-flop between 16 bits and 8 bits?
I think you could. Yeah. The other thing that you can do on the RP2040 is, I believe it's the case, I have to double check this, but I believe it's the case that you are limited to as many as 16 bits here, which is to say not as many as 32. I'm like 90% sure of that. But because of that, the buffer on the SPI channel, what you can do in that case is load up 2 16-bit transactions, and they'll be sent one right after the other. If you don't raise chip select between those 2 transactions, the secondary device can interpret the received information as a single 32-bit transaction. Other questions about SPI? Okay. So then, essentially my plan, incidentally, is just get through as much of this stuff as we do. However far we get is fine. The next thing that we talked about was direct digital synthesis. I'll just pull this up for a moment. Which is an algorithm. So it's not specific to the RP2040. And I'll just remind you that the central notion at the core of this algorithm is to realize that if we come up with a new unit for angle, so instead of degrees, instead of radians, we come up with a new unit for angle, which we've been calling accumulator units, and we decide that in one rotation there will be 2 to the 32 of those units, then what it allows for us to do is store that angle in an unsigned int, which contains 32 bits, and if we add some amount to the variable that we're using to represent that angle, that is isomorphic to, which is to say it can be thought of as, or is the same as, rotating this phasor. And we can add and add and add and add, and because we've decided that there are exactly 2 to the 32 units of angle, units of accumulator in one rotation, we can add until that thing overflows, and it just works. When it overflows, we land back at the correct orientation of the phasor. That's the central abstraction for direct digital synthesis. And then the puzzle is, okay, suppose that I want to synthesize a sine wave of a specific frequency. each time I enter my synthesis interrupt service routine, by how much should I increment that unsigned int that I'm using to store my phasor angle in order to generate an output waveform of the desired frequency. And what the direct digital synthesis algorithm tells us is exactly that. In particular, for some sample rate fs, in your case it's 40 kilohertz, and some desired output frequency, in your case it's 2300 hertz, frequency of a cricket chirp, this formula allows for us to compute the amount by which we should increment our accumulator variable every time we enter the interrupt service routine in order to generate exactly that frequency. So we saw this, for instance, in this example, where every time we enter the repeating timer callback, we increment the variable that we're using to hold phasor angle by this value phase increment main, which we have computed to be whatever it needs to be in order to generate an 800 hertz wave. So we increment it by that amount, and then we use the top 8 bits of that accumulator to index into a sign table that's 256 elements long. Like we talked about, it wouldn't have to be 256 elements long. It could be longer, in which case we would have less harmonic distortion, as you may recall. It could be shorter, in which case we would save ourselves some memory, but we would have more harmonic distortion. With a sign table that's 256 elements long, you may remember that our first error harmonic in any synthesized sine wave is at higher than audible frequencies, so you will not hear it, and highly attenuated, so you definitely won't hear it. Okay. Any questions about direct digital synthesis? Folks seem to be relatively okay with this one, actually. It's a good one to know. Okay. The next thing we talked about was multicore. And let's just look at a simple multicore example. And I'll remind you that in a program that in a multi-core program, that is to say, in a program where you are running code on each of the 2 processors in the RP2040, you will generally expect to find, the structure of the program that you'll expect to see is probably something like a bunch of includes that bring in all the SDK functions that we want to use. In this case, we want to talk to the SPI channel, and we want to use multi-core, so we're bringing in the relevant includes. And then you'll find a whole bunch of global stuff, maybe some macros, maybe some global variables. And then depending what you're doing, you may find a couple of interrupt service routines. In this particular example, there's an interrupt service routine that's running on core 0 that is synthesizing beeps out of core 0. And then there's a second interrupt service routine that's running on core 1 and it's synthesizing beeps out of core 1. And then we'll find some function that plays the role of main on core 1. When you're on core 0 and you launch core 1, you specify the argument to the function that launches core 1 is the name of a function. And that is your entry point on core 1 in much the same way that main is the entry point on core 0 for you. It's the place where your code starts executing. So you'll expect to find some function that's playing the role of main on core 1, and then you'll expect to find main. And in the examples that include proto-threads, it may be the case that what main does is set up and configure a bunch of hardware peripherals, and then add a bunch of threads to the scheduler and start them. And then you'd find a bunch of threads declared up top. And likewise for core 1. It may be the case in a threaded program that this core 1 entry point, all that it may do is perhaps configure some of its own hardware peripherals, and then add some threads to the scheduler and start the scheduler. And the scheduler that we're using, it's been modified by Bruce, so it is intelligent enough that when you add threads to the scheduler on core 1, it knows it's on core 1. So when you start the scheduler, the only threads that are being scheduled on core 1 are those that you've added on core 1. And likewise for core 0. The scheduler knows whether it's on cores 1 or 0, so any threads you add to either core run only on those cores. If you want for the threads that are running on the 2 cores to communicate to one another, there are strategies for doing that. You can use those spin locks. And in particular, Bruce has added some multi-core capability to the proto-threads API that allows, for example, for sharing of information between cores using the FIFO that sits between processors 0 and 1. Okay. Folks seem to have a pretty good grasp on the Cricket state machine, I think. So let me then talk, folks seem to have a pretty good grasp on fixed point as well. Let me spend the last 5 minutes or so one more time talking through chirp synthesis. And I want to reiterate one more time a strategy that you might consider employing for doing this. So what I mentioned last time is that I think an appropriate way to think about chirp detection is you can think about 3 processes taking place. You can think about one cricket being synthesized, the other cricket being synthesized, and an FFT being run. If you were careful, you could set this system up such that an FFT were running on each core, but I don't think that's necessary. I think you only actually have to have the FFT running on one of the cores. So your code will look something like setting up and configuring a timer interrupt on core 0 that synthesizes cricket chirps, doing the same on core 1 that sets up and synthesizes cricket chirps, and then having a thread that runs on either core. Suppose you just run it on core 0, because that's what the example does. What this thread will then do is gather a batch of ADC samples, compute an FFT on that gathered batch of ADC samples, and once it has computed that FFT, it will look for the frequency with max power, and it will ask, is the frequency with max power the one associated with crickets? If so, it then knows, okay, there is a cricket chirp present in this batch of samples. It then has to ask both core 0 and 1, is it possible that you generated this cricket chirp? And the way that it can learn that information is by accessing the state variables in the interrupt service routines of both core 0 and 1. Those are global variables, so they're accessible to both cores. So what I would recommend is in line 240 here, this is where you start gathering a batch of ADC samples. And you know exactly how long that's going to take because you're gathering 1,024 samples and you're doing so at 10 kilohertz. So you can figure out how long that is in milliseconds. You can figure out how long that is in timer interrupts, right? So you know exactly how long you're going to be gathering data. Right before you do that, you can go check the value of the state variable in core 0's interrupt service routine to see which state is core 0 it is in. Is it in the long pause between chirps? Is it in the chirp synthesis state? Is it in a syllable producing state, right? So you ask which state are you in, and the other piece of information you ask is how much longer are you going to be in that state? Because like I mentioned last time, because it takes a long time relative to the other processes going on here, it takes a long time to fill up that batch of ADC that ADC buffer. It is entirely possible that the state of your crickets change from when you started gathering the ADC buffer to when you stop. So if you only asked for the state of each cricket when you started gathering this, core 0 may say, I'm not producing a cricket chirp, but then right after you start gathering the batch of samples, it starts producing a cricket chirp. So you'd have a whole batch full of core 0's cricket, but you would be under the impression that core 0 didn't produce that cricket chirp. So you need 2 pieces of information from each core. Which state are you in, and how much longer will you be in that state? And if either core reports that it's in the chirp pause state, which is to say the state of silence between chirps, and furthermore, it reports that it will remain in that state for as long as it takes to gather a batch of ADC samples, then that core is eligible to detect a cricket. Because you can be absolutely confident that the batch of samples that you gather will not include any chirp data from core 0. If it reports otherwise, then that core is ineligible to detect a cricket, because if you detect a cricket in that batch of samples, it's entirely possible that it was generated by that core. So as I mentioned last time, we're not detecting the start of the cricket here. So what that means is next week, when we look at your synchronization, they aren't going to perfectly phase lock. they're going to slide around to within the length of a chirp, and that's okay. It's okay because it sounds good. It sure sounds synchronized to our ears. And furthermore, it's okay because I think that kind of maps to the biological system. Real crickets aren't synchronizing to within, one cycle of this CPU. They're synchronizing to within about the length of a chirp. Okay. Does that make sense? So it's a challenge, right? But the reason I kind of like this as an objective for you all is you really got to think about all the processes that are going on here and the relative timing between those processes. It's a good problem for thinking about that. It's challenging, but I think it's a good one for really thinking about concurrent stuff. Okay, that's all I've got for today. Come to lecture on Wednesday because it's going to be a special guest on Wednesday.